the two different areas, PG grading and super, that is based on the material. And mechanistic empirical design, ASTO 1993, Asphalt Institute method, these are all pavement design, right? So the first one is how you select the cement, how you select the concrete, how do you select the brick. Second one is how do you build the house. Do you see the difference? So PG grading is a important component of asphalt material selection for a certain temperature range, certain climatic condition and everything. Now after that, what do you do? How do you design your pavement? That's not PG grading's problem, right? So you are right now what you are studying is the material selection in your MTech courses and stuff. And here we did not go into material selection. We didn't go into viscosity grading. We didn't go. We're just saying, we're just assuming that you select the appropriate type of material. Like I'll give you an example. In America, everything is PG grading, performance graded. But in China, it is still penetration grade. It's something called advanced penetration grade. It is not the basic one, but they have done a lot of research, but it is not PG grading. It is not PG whatever and stuff. So yeah, that's basically two different domains. Yes, exactly. So how do you determine the thickness is, again, my example is how do you design the house, right? How thick of a slab do you need? So you have a load, and then so let's just simplify everything. Let's just make it a beam, a cantilever beam or a simply supported beam. You apply point load, you know the deflection formula, right? So it's that's what forward calculation is we were talking about. So you do the exact same thing. How do you determine the thickness is by saying that I'm going to assume this thickness. I'm going to learn something called multi-layer elastic analysis, which is what this IIT PAVE and everything is. And then you predict stresses and strains, and you say, no, this strain is too much. I need to go lower than that. So I'm going to increase the thickness. No, this strain is way too low. I'm over designing. I need to reduce that and stuff. So it's an optimization process after that. So it's basically application of mechanics to determine thickness. If you go into mechanistic empirical design, in ASTO and stuff, it is all based on empirical, which is something called and number. So a structural number is basically who remembers the formula? Others, come on, PhDs. Sn equal to A1 D1. There you go. Okay, plus A3 D3 M3. So I can't go over all of this right now. So A1 is like a structural, it's called structural coefficient. Okay, so it's basically how good your material. So let's step back. Remember what I said, the old pavement design methods were all about protecting the weakest layer. So in ASTO, you're basically plugging in the resilient modulus of the layer and stuff, and you're saying how much pavement I need on to protect. And that A1 is for asphalt, it is what, 0.44, something like that. And for base, 1.08, something like that, for subbase and stuff. So you are saying every inch of asphalt has this structural coefficient of 0.44. So if it is 2 inches, it is 0.88, right? Let's just say you need a total of whatever, 5 or something. So you have to have a combination of this and this. D is thickness and M is drainage. Let's just simplify it and make it all one. Then you calculate it that way. So that is how the calculation is done. Now your question is very valid. Is this 0.44 valid for all binders I use, for all mixed designs I use, for SMA, stone mastic asphalt, for dense graded asphalt, everything? The answer is no. But that is what you get in empirical design. How do you have somewhat improved empirical design. Let's just say 0.44 is 1. Let's just say now in the state of Odisha, you have done so much research and so much data collection. You can say, okay, use 0.44 in this kind of a pavement. If I have a really good binder, really good thing, then maybe use 0.46. Maybe if you have a really poor aggregate and everything, maybe make it 0.4. Now what you're doing is you're building on top of other empirical methods with experience. Do you understand? So that is what the pavement design component is. What you are talking about is only about material. So that material constitutes this, right? On in mechanistic, what did I say? Delta is equal to function of load, thickness and modulus and Poisson's ratio, I said, right? So your material that you're studying, your PG grading and everything is contributing to this and this. So you determine these and then you do this and this. So well, this is known already, this is the demand. The D is what you determine so that your delta is in a stable range. This is forward calculation right now. Delta is equal to this is that. So if you have an existing pavement and you are measuring delta, then it becomes back calculation to determine E.
Like this is part of your mechanistic design part. Okay, mechanistic empirical design. One significant part is material
Okay, so good question. A forward calculation is basically when you have all your properties and you are trying to determine response. Okay, a back calculation is you are missing some property but you have some response measurement. So now you are using the response and some other properties to back calculate or to determine the missing component. This is how a traditional equation looks, right? Let's simplify everything. Talk about a simple beam. You have taken structural analysis. I know that, right? No, but you have passed undergrad, right? Yeah. So in undergrad you took that. I'm sure you did. If you didn't, we need to talk. So that's delta, right? That's deflection. Is a function of the length of the beam. There is E and I terms and everything, modulus and moment of inertia, and there is the load. So all of that is your delta. That's the forward. Now let us say in a beam, I'm saying that I know load, I know deflection, I know I, which is I is a geometric property. I don't know E. Can you calculate E? You just rearrange the terms, right? That is back calculation. No. ME design is a forward thing. Back calculation is when an pavement exists and you are trying to determine its properties, right? Again, I don't want to confuse you, but back calculation has nothing to do with ME design. It can be anything. Back calculation is taking some kind of a performance, use predict or some of the properties that you should already have. You understand? Let's say, okay, it's a silly example, but let's just say you are a asphalt engineer on an agency. You have all the tests, you have run all the tests, you have all the properties, but then you go on vacation, right? Now somebody else comes and tests the pavement and says, rather than waiting for me for Pushpak to come back so that he can give me the value, I'm going to determine just by measuring the deflections, I'm going to be able to calculate what properties he established. That's back calculation. The only problem is there is no Pushpak in the real world. Nobody has run all the tests. So that data is missing. So that's what you're doing. And the data is not just missing. I mean, it's constructed data. Like sometimes, I don't know how much you all are, some of you I'm sure are familiar with construction practices. You specify 50 millimeters. The actual construction is sometimes 45 millimeters, 52 millimeters. I mean, it all depends, right? So that is going to change your response of the pavement. That's what back calculation. Good? Better? Okay. We can talk more. I have no problem if you just come and sit down with me during lunch to have questions or something. I love talking, so it's not a big deal. Any other questions, guys? Some couple of you sent me on WhatsApp your more circles, and you were having issues because they were just concentric things and stuff. Did you fix it? Not yet? Okay. Either find me during the break or something, I can talk to you, or somebody like Atanu or somebody, can you just help them? Anybody who solved it, just take a look at it and stuff. I am pretty sure if it was, you're probably not taking the central coordinate and adding it. From my screenshot, I didn't go into details of that. But anything. Any other questions? Sorry about my voice. I got some kind of a allergy attack at about 5 a.m. today. I started coughing and stuff, and I had to take a medicine. We'll see what happens. I think I'm 5, but we'll see. We have a very, very, very fun day today. That's what I told you yesterday. We're going to start repeated loading. Okay, and today is all about resilient modulus. We're going to go into the details of the procedure, the mechanics, the test procedure. We're going to analyze different aspects, and then we're going to go into resilient modulus model fitting. What is a model? How do you fit your test data to different models? What are the model parameters telling you? What will you give there? And in the tutorial today, we are going to do two things. One is, I was able to find that back calculation algorithm that is on Python and Google Colab. So the good news is you don't even have to install Python. It's a Google Colab thing. We'll just launch the software and we will together run some cases. I want everybody to run with me so that we will see what's going on, how the back calculation is working. So we're probably going to, if my throat survives, I'm going to probably extend the tutorial a little bit today, because and then I'm going to give you some resilient modulus test results, and we will do an Excel exercise of fitting models, determining model parameters. Okay, and then I can show you how to do it in MATLAB or Python again, and we'll go to that. So lot of fun stuff. Please ask questions. Quick question: resilient modulus testing. How many of you have done? That's a big number. I did not expect that. Okay, that's greater than I have ever had in any class. Okay, so you all are on the hotspot. I'm going to ask you a lot of questions, right? So you're going to answer, especially Tanmay. You are developing a device. You have no excuse. Okay, the Menti link, you may or may not want, yeah, scan it. I don't have much done today because it's a little bit of a different class, but we'll see. We'll use it most likely. We'll have some inputs and stuff. Okay, repeated loading, resilient response. Do me a favor, can you come here for a second? Hold this table with me. I want to move it there so that I can keep my cup, because, oh, the cable, okay. I just want to keep it here. I put it on the desk and it crashed. Thank you. Yeah. Is it? Sorry? Huh? Out there? Okay. Good, everybody? Okay. All right. So repeated loading. Okay. We are going to talk about repeated loading and repeated loading response and stuff, and we will see what is resilient modulus. I touched on it yesterday a little bit, so we're going to build significantly on that. So there are several ways of you visualizing this. I told you already what is repeated loading, and just for documentation purpose, if it was a cyclic load, then you would have this, right? In a pavement, you are not really applying tension to the material, although you can argue that, when you have the repeated load, the moving wheel load, there is a little bit of extension happening, but it's not really a cyclic loading. So we don't call it cyclic, we kind of remove all of this, right? Then the question is it just a mod of sine, the loading pattern? If it is just a mod of sine, if the question is, if it was mod of sine, what would happen? This thing would just flip over and then you would have this, right? But that's not how a pavement is loaded either, right? So we use something called a Haber sign. We will get to that. Okay, the loading pattern is known as Haber sign. A lot of people will say, half sign. The answer is no, it is not half sign, it is Haber sign. There is a difference. Okay, we will get into that later. Now let's take a look at what is repeated loading and what is happening. I told you that when a pavement, when a soil element is here and you have a wheel moving, then with time it will have 0, 0, 0, and then you will have some kind of a load pulse, because the traffic, the influence zone, it basically moves from one side to another and stuff like that, right? So that's your load pulse. The question is, you have many of them. So if you look at the time series of the loading pattern on any soil element, then it will basically look like you have this, there is a little bit of a rest period, there is a little bit of a rest period, there is a little bit of a rest period, and stuff like that, right? So there is loading happening and then there is unloading happening. So now let's go to the stress versus strain domain, right? So if you go into stress versus strain domain, this is epsilon, this is sigma. We are trying to load this and then we unload this, and then at beginning there is going to be some kind of plastic deformation, right? So this is written as epsilon P. Epsilon is strain, P is permanent plastic, whatever you want to call it. Then you are going to go load again, come back again, there is going to be some, so maybe this is P1, you now have another epsilon P2. Keep going forever, long time. After some time it's going to become what is known as hysteretic behavior. Whatever goes comes down, comes back. There is no additional energy dissipation happening and stuff like that, right? This amount is called the total permanent deformation that was accumulated on the sample because of all the loading and everything. Then is the recoverable part, or epsilon R, or resilient strain. Okay, resilient strain is here, and then this one, this stress that you are applying is basically the deviator stress. Don't say cyclic stress, repeated stress, but deviator stress, right? So MR, or resilient modulus, is defined as sigma d over epsilon R. Okay, graphically it is the slope of this line. Okay, this is where the basic understanding, and these are questions I usually ask for MTech final exams, PhD qualifier exams and stuff like that. If I am on a committee, I always ask things like, what is the difference between elastic modulus or Young's modulus? Can talk about if you can change it to steel or something. How does it look? It looks something like this, right? You have this and then you go something like that thing, steel. So but you can still define a E here, right? The question is, what is the difference between E and MR? Let's go. Load is monotonic. Okay, so you are saying if I change this to load, unload, load, unload, load, unload, load, unload here, then that difference will be taken care of. Viscoelastic, I don't know. I mean, it doesn't have to be viscoelastic. It will have some information. So there is the elastoplastic, but if you look at it, even steel is elastoplastic as well. Beyond a certain region, beyond the yield point, it's going to have a plastic behavior. Okay. Okay, that's first. Yes. So that's recoverable strain only under repeated loading. But I mean, that's the right answer partly. But if you look at it here, the sample here does not know anything about recoverable or plastic. For here, it is all elastic, right? So I mean, that's true when you know the whole picture, right? I know I'm picking here, but that's the whole point of understanding it from a mechanics point of view. Where is elastic modulus defined? At what strain level? It's at zero strain, right? It's at the initial thing. There is no deformation induced in the subject or in the material. Here you have already accumulated permanent strain. So it is not at the x is equal to 0 location. It's not. Okay. Now let's go back to the definition of modulus. What kind of a modulus is it? Hint is mathematics, or like graph theory. Tangent modulus. It's a tangential modulus. You're drawing a tangent to the stress strain curve. What are you drawing here? It's a secant modulus, right? So it's a secant modulus. It doesn't have it's not just a tangent and stuff, right? And the third one is, yes, it's defined. This is defined under, usually defined under monotonic loading. This is always defined under repeated loading. Okay, so these are differences that you should know. Why it is not why is resilient modulus is not just a Young's modulus said in a different word, in a term. It's different, right? So we're going to define this. The question is, it's actually a discussion we had a little bit this morning. The question is, what is happening here? What stages are accounting for this in a pavement? Say again? Before traffic is applied, which is what? The compaction, construction and stuff. Ideally, if you have a really well designed and well constructed pavement and stuff, you should have all your permanent strains accumulated, or that's what's called the conditioning of the sample. We'll get into that, the conditioning. Some people call it shakedown and stuff of the sample before you hit the resilient part, right? So repeated loading is going to have two different responses, and there is a way to to plot it in another way or another form, what I'm going to do is I'm going to just say number of load application or something on the x-axis, and I'm going to call this as deflection. Okay? What happens is when you first apply the load, deflection increases and then it actually goes down. Actually, rather than this, maybe change this, folks. Let's make it time. It's going to be better. It's going to look better. Let's make it time. It goes up, it comes down. Then after some time, it goes up, comes down. After some time, goes up, comes down. It will happen, it will keep going a little like this. It will not come down all the way. It will go like this, and then there will be a stage when it will become completely recoverable. Now if you take the bottom points of all of these graphs and you draw this, that becomes your delta P or permanent deformation, right? And everything other on top is the recoverable part. So if you put an LVDT on your specimen, what are you going to measure? Which mesh deflection? The vertical, which is the total, right? You're going to measure the total. So for every cycle, if you have to calculate a resilient modulus using instrumentation data, it's not as trivial as just taking the deflection and measuring. You have to find out that cycle, was there any permanent deformation accumulation. You understand what I'm saying? So like this, what you have to say is, if it started like this, did it come back to 0 or did it actually do something like this? Because if you just take total deformation, folks, you're going to divide by this whole amount, but you should actually be dividing it by this amount. Does that make sense, what I'm saying? Yes? So that is why resilient modulus devices are very specialized, because they are not just measuring a total displacement, they are actually keeping track for every cycle, the initial value, the final value, and the maximum value. And the resilient is the maximum minus the final, not maximum minus initial, because if you do maximum minus initial, you're taking the total deformation. It's a little bit detailed into test design, but that's what it is. Okay, so you know that every transportation infrastructure is loaded repeatedly, and that is the reason you have to measure your resilient response. So this is a video that I use to teach. This was actually based on some old FHWA video that was made. So for any element, you have as the truck moves, your elements start deforming and then they start bouncing back and stuff. The whole idea is that it should be completely bouncing back when you're operating. Otherwise, you're having what? Rutting, permanent deformation, which manifests itself as rutting, right? You don't want that, right? So this is basically stress versus strain under repeated loading. Again, this is the acknowledgement side. I took a lot from Professor Tumler and stuff, and the whole idea is that it holds for both pavements as well as roads. This is probably the first time I'm showing this to you all. I don't know, those of you who are not familiar with the cross section of a railroad track, you have the rail, you have the tie, sometimes you call it sleepers in Europe, and in India you call it sleepers. In North America you call it cross ties. Then you have what is known as railroad ballast, which is the coarse grain. So basically below this, folks, you can think of this as base, subbase, compacted subgrade, natural subgrade kind of stuff. similar stuff. Gradations are different, material is different, load levels are different, thicknesses are different, but the mechanics is exactly the same. There's no difference. So we're going to take a look at this. I talked a little bit about yesterday. You have a confining stress, and then you have a deviator stress coming from the top that actually makes it sigma V. This makes it sigma C, and then if there is no shear, if you are directly on top of the sample, then they can be replaced by your major and minor principal stresses, right? So it's not always the vertical major principal stress, horizontal minor principal stress is true only when the load is directly on top. If the load is moving, the directions have changed, right? So you need to remember that. So that's what triaxial testing typically does that. We talked about this a little bit. There is no shear on the boundaries, and that is the reason we are able to fit principle. Otherwise, it's not true. So be very, very sure about this. Okay. Then there are some other things that we are going to define. One is called bulk stress, or it is also called the first stress invariant, and bulk stress is nothing but sigma 1 plus sigma 2 plus sigma 3, and it is written as a symbol theta. Okay, so it's bulk stress. So bulk stress, if you go into mechanics, it is also called first stress invariant. That's theta, that is equal to sigma 1 plus sigma 2 plus sigma 3. Okay, let's look at a triaxial device, right? What is the relationship between sigma 2 and sigma 3? They're the same, right? So we write it as sigma 1 plus 2 sigma 3, right? What is the relationship between sigma 1 and sigma 3? Sigma 3 plus sigma d plus 2 sigma 3 . Theta is sigma d plus 3 sigma 3. Why am I telling you this? Because this will become very, very useful as we go into the model fitting and everything. It's going to become very, very relevant for you, right? So that's called bulk stress. There is another thing we are going to define called octahedral shear stress, but we'll do that later. It's when the time comes. Okay, factor of interest. Repeated loading, I accidentally wiped that, but you saw that in the same plot we were getting this and we were getting the thing, right? So repeated loading gives us information about both resilient modulus and permanent deformation. Only difference is permanent deformation test, which we will cover mostly tomorrow, and among other things, they'll run for a lot longer. Permanent deformation tests are done under 1,000,000 cycles, 10 million cycles, at least 10,000. The longest I have run for a paper was 10,000, not longer than that and stuff. And that gives you rutting. Materials, we're going to talk about cohesive soils and cohesionless or like granular materials. They are different. They behave differently under repeated load. Okay, and we're going to talk about testing approach. This is a typical data that you would obtain, deviator stress versus actual strain, for a granular material. And do you see how these shapes are concave up, like how they are like a saucer upward, not the traditional way of plotting? That is because for these materials, as the stress level increases, which is also as the strain level in this case increases, the modulus actually increases. Do you see what I'm talking about? Like if you do a tangential modulus here, you do tangent, 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 the tangent actually keeps rotating up, right? So the modulus value increases, right? So that's called a stress hardening material, right? Because it is a stress hardening is basically you're going to have the tangent rotate upwards. If you had a stress softening material, which is what I drew because that's the most common one when you are explaining the concept, you have the curve going this way. So if you draw a tangent here, 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 it's rotating downwards. Does that make sense? Some of you, it may be completely first time you're exposed to. Please stop me. There is no harm. You know, this is important stuff for a transportation geotechniques class and stuff. So I've told you this. We're going to go get into test procedures, but this is a good picture to understand. Remember what I told yesterday about LVDTs and how they measure deformation and stuff? Okay, let me ask you a little trivia. I was talking about shear strength testing yesterday, right? We talked about shear strength testing. If I ran a shear strength test on this sample, what will happen? Experimentalists will know this immediately. Theoretical people will have to think a little bit more. There is a simpler answer. I mean, yes, mechanically, but there is. I'm looking for a simpler answer. Will break. Your LVDT will break because you are on the sample here, right? It's going to bulge. You're going to ruin your LVDT. Your advisor is going to be extremely pissed at you, right? So what I'm trying to say is shear strength testing, you usually don't do on sample deformation measurement because your LVDT is going to break. That is the reason yesterday when you did the data analysis, we were talking about the actuator LVDT. And that is the reason the axial LVDT 1, 2, 3 and radial LVDT data, that was all 0. Do you understand? Because we didn't mount it because it would break. If you do a resilient modulus test, we are now talking about strain levels that are significantly lower than the failure strains and stuff. Now we have all sorts of instruments. Did you raise your hand, Pushpak, or no? So now you are just mounting it around the sample now because you are now interested in the deformation, in the strain levels and stuff, right? So on sample, yes. Can you say that again? No, Haber sign is not. Okay, good point to get to that. Haber sign is this. There is something called Ver sign. A Ver sign is 1 minus cosine theta. Haber sign is divided by 2. And those who are in good at trigonometry and stuff, and if you still remember, what is cosine 1 minus cosine theta? Yes, 2 sine square theta over 2, and now you're dividing it by 2, so it basically sine square theta over 2 is what your Haber sign is. Now if you're asking if this is a Haber sign, this is a hand drawn schematic. I have no idea what it is. It is nothing. It's no sine square. How will it be negative? Oh, no. So there is a rest period. In always resilient modulus testing, there is a rest period. We'll get to that. What's the rest period? Why it is what it is? We'll get to that. But no, it's not continuous in resilient modulus testing. Okay? So please remember these, folks. And why is this important is when you are designing a test setup, saying that telling the controller, you're doing a lab view coding or something, to tell the controller this is how much load you're applying, you're going to do this mathematics. You're not, if you do like sine mod or something, the magnitudes are going to be wrong, right? So you have to pay attention to these mathematics. Now, is something going to be in all practical purposes, if you go and work for a company, is this going to be very useful to you? No. But this is what you should know when you are doing a PhD or something. You need to know that what's going on rather than just go on the surface. We talked about this, right? Major load bearing layer for pavements and railroads and stuff. So we need to have one of the design input is layer modulus. Okay, so this is another pitch for things that we have talked a little bit about. How do we do construction quality control in the field? Density. What do we use for design? What is the relationship? Nobody knows, right? So can you do modulus based compaction? Now that's a very open-ended question. There's a lot of discussion in that. There are ways, but it's very complex and stuff. Why does nuclear density gauge even exist? Because it is very fast and it is reasonably accurate as well, and it gives you both moisture and density, right? If you do sand, are you familiar with sand cone tests and stuff? Sand cone test, if you do stuff like that, it will only give you density. You still have to put it in the oven to get your moisture. Nuclear density gauge gives you both of them and stuff, right? That's a little bit sidetracked. So we talked about this. We have to modulus testing. We can do indirect IDT in asphalt as well to do MR testing. In asphalt, MR is not as common. It is more dynamic modulus that is more common, right? But excuse me, because dynamic modulus is what is known as a complex modulus. It's not just elastic part, but there is. We have already done this, so you know this what I'm talking about. This is the stuff that I tell you about. There are many modulus values that you can determine when you have a stress strain curve. There are many definitions of modulus. There is maximum modulus, there is at certain strain values and stuff like that. But what you are trying to do is you are actually trying to draw in a resilient response, you're trying to draw a secant modulus between for only the recoverable part of the hysteretic loop. So that's the definition of resilient. Okay. Rapidly applied loads similar to those from wheel loads. So let's stop here, and then now we talk about rest period and stuff like that, right? So rapidly applied loads similar to what is done with wheel loads. So how would you do that? Let's pick one of the initial MTech students on that side. I haven't. So you guys are, you said, on the first year and stuff. Okay, so let's I want to ask you, and it's open-ended, so I want you to use your brain, not your previous knowledge. Just think. Okay, I am asking you that tell me what kind of load a soil layer 1 foot below my surface, a soil element is experiencing on this road, on this national highway. How would you determine it? What would you do? And you have all the resources in your hand. I'm not restraining you. You have everything you need, every equipment, every mathematics, everything you need. So how would you determine experimentally what is the stress, or what kind of a stress pulse a soil layer 1 foot below is experiencing? Experimentally. Well, we can go back to calculating deformation. I don't think you can do that to calculate pulse, but let's not worry about mathematics. We're talking about experiments. And I said you have all resources. You're not restricted to what you have in your current lab or in your current pocket. You have everything. What do you do? What would you do? You want to phone a friend? Somebody else? Geophysical. Okay. That tells you the speed, yes, and then what? Frequency of the load. It's actually, maybe I didn't ask it proper, the question, because it should be a relatively simpler answer. Sensor, pressure sensor. So he knows a little bit about probably sensor, so he's like pressure. But the point is, those of you who don't know anything about pressure sensor, you have to have some kind of a sensor that is going to tell me the time versus pressure data, right? Agree? So we are putting on this pavement two pressure sensors, here. Can be pneumatic, it can be piezoelectric, it can be vibrating wire. Vibrating wire does not work very under dynamic loading, but yeah, it can be anything. Technology does not matter. It can be servo hydraulic. You can have a air based system where as the system goes, air gets pumped out to something. Anything. Sensors are sensors, right? So what do you do here? You have a thing moving like this with time, right, folks over there? Time, you have, it's at the top, so it's coming, and then it has some kind of a pulse, goes down. The bottom one, probably coming, some kind of a pulse, goes down. Why is it wider? Because the stress dissipation works like this. So this one, even when it is here, this element is feeling the stress, whereas this element is not feeling the stress. On the other side, it's exactly the same, symmetric and stuff, right? So that's the reason as you go down, the stress pulses become wider and shorter, less magnitude. As you go to the top, narrower and taller. Now the question is, you have a layer like this, HMA, base, subgrade. Somebody who knows resilient modulus testing, you have run it, right? What is the rest period you use? What is the pulse and rest period? Do you remember? 0.1, 0.9, right? 0.1 second. We'll get to that. People who don't know, we'll get to that. Don't worry. 0.1, 0.9. Is that for base? Is that for subgrade? Is that for everything? Is it for 2 inches below, 5 inches below, 6 inches below? Where is it? Asphalt layer? No, you don't run resilient modulus test on asphalt. I'm talking about ASTO T307, which is what we're going to go, like the actual testing that we did with the lab. For granular, have you done subgrade testing? How many of you have done aggregate versus subgrade? What? You have done aggregate, I know that. How many of you have done subgrade soils? What do you do? So one of you is wrong, right? The code says the same, so that's our excuse, isn't it? So the point is, it's if you actually go and track the rest period and the pulse width, it should change depending on where you are in the layer. If you look at the code, the subgrade, yes, it is acceptable to do it at 0.1, but it's actually also recommended to do at 0.2 and 0.8 in ASTO T307. Whereas aggregates are usually 0.1 and 0.9. That's the reason, because they are above the subgrade and the pulses are going to be a little narrower. And the stress states are different for sure. That we all know, we all agree and stuff. So the width is going to be different. That's one thing. But again, we have to pick something. So they had to pick something. What does the width depend on? Pushpak, what does that width depend on? Like this thing, I said I put a sensor. One thing you already know is the depth. We know that. What is the another thing I did not tell you? The width depends on. No, the width, not magnitude. I'm not talking about this. I'm only talking about the time domain, time axis. What does it depend on? Speed. Speed of the vehicle, right? If the speed is very high, it is going to be very short. If it's much higher, it's going to be much lower, then it's going to be much wider, right? So now you're talking about 0.1 second versus 0.9 second. What speed does it correspond to? What speed is it? 80, 45 to 50 miles per hour and stuff. Do you always drive on 80? So should you always drive on 80? So you have to again set codes for certain values, right? So it was just done by research and stuff, and they develop it for 45 to 50 miles per hour, which is 80 kmph essentially, right? Why the rest periods? Yeah, there is a gap. There is a gap between the load, vehicles and stuff, right? So rapidly applied loads. What is rapidly applied? 0.1 second is the load pulse, 0.9 second rest, then 0.1 second, 0.9 second. So in another very important question, because these are things that, you know, this course is also supposed to open or give you directions for, you know, looking into problems, future research, or exploring and stuff. Do you know what frequency of loading is? You know that, right? Right? A sine omega t and stuff, you know what the frequencies and everything, right? Omega is what? 2 pi f, right? F is frequency, right? So what is the frequency of loading when I have a sinusoidal wave of this and this? Hold on, don't say anything yet. When the time period is, this time period is 1 second. What is the frequency of loading? 1 hertz. 1 cycle per second. Everybody agrees. Now I am doing this 0.1, 0.9. What's the frequency of loading? Is it 1 or is it 10? How much are you loading actually? Are you loading it in 1 hertz, 1 second, or 0.1 second? 0.1 second. So it should be 10 hertz, right? Yes, but how, I mean, when you're loading the sample, does it really know that a rest period is coming? It doesn't, right? So is it 1 hertz or is it 10 hertz? Nobody knows. There is actually no agreement on that, right? People have talked about it different ways. So frequency of loading, when you have a repeated loading, is not a trivial matter. It's not a circle that you can just define, cyclic loading and stuff like that. It's not, right? And how does it affect speed versus that? Because, oh, by the way, one more thing I did not say, I think I should say, because we are now getting into the details. We talked about this width depending on speed and depending on depth. What is the other one I left out? Say again. Upper layer stiffness, not the same layer stiffness, the upper layer stiffness. Why? Because that determines at what angle is this load is going to get dissipated, right? Sometimes people will say it's 45 degrees or something like that. That also can change, right? So your modulus or the load pulse can change between a summer and winter when your asphalt layer changes stiffness or modulus by a factor of 10, like 400,000 psi to 4 million psi. It can happen, or 2 million psi. So your pulse width is also going to change, right? So rapidly applied loads similar to those from wheel loads. So you're trying to do your best job to simulate that. Relates to elastic component of response only. We talked about that. We're taking care of the plastic. We're eliminating the permanent. What is the difference? We talked about this already. Lab test, ASTO T307, which came out of Sharp P46. It can be done under undisturbed, disturbed, or something. So when you are in geotechnical, like pure geotech, undisturbed sampling is a very, very big deal, right? In pavements, it's not. Why? Yes. It's, yeah, harder does not mean we should not do it, right? Harder, difficult to get an undisturbed sample, but if the geotechs can, we can too, right? But the point is, the answer I was looking for is when you are doing a pavement construction, you are anyway compacting, you're anyway mixing it, you're anyway scrapping it stuff. So it is always reconstituted, remolded, and stuff like that. So there is no, it's not really undisturbed in resilient modulus test. So there are different protocols. There is ASTO T307. There is something called harmonized protocol. We'll go into that a little bit. And then we are going to, you can also do correlations. And mostly, I can guarantee that when you go to practice, even in India, it's mostly about correlations and other relationships, right? I'm pretty sure the agencies don't run it very regularly. Nowhere they do. Even in America, most of the agencies don't run it regularly. Okay, so it's a fundamental problem. Well, here, I mean, this is just some survey results. How do you determine what kind of laboratory specimens? There are some people who actually did undisturbed from rehabilitation designs, laboratory fabricated mostly and stuff. The fundamental property, it's a rational test. It considers the effect of density, grading, fines, shape, water content, all of that. So you can actually represent your actual soil or your aggregate, and then you test based on that, right? And end result is you should provide a value to your pavement design or your pavement rehabilitation, saying this is what you have, and then you go from there, right? So then let's talk about the test procedures. The primary one we are going to focus on is what is known as ASTO T307, right? So T307 is it has two types of materials it considers. They are called subgrade soil, unbound granular materials, and or type 1 and type 2 and stuff, and we'll look at that. And the test procedure or the test method is slightly different between the two, and we'll, in terms of magnitudes and stuff, and we'll go into that. First of all, conditioning. You have a reconstituted sample that you compacted in the lab, right? And then you're going to test it. So that's basically, before you get into resilient response, you have to have your initial compaction done, right? What is that simulated through? That is simulated through your lab compaction, and anything remaining you should be doing what is known as a conditioning stage. Compaction vehicles, are they heavier than regular trucks or lighter than regular trucks? Heavier usually, and they are running directly on top of the layer, whereas trucks are running on the asphalt layer or on the concrete layer, which is dissipating the stress. Is conditioning, you should be applying definitely greater magnitudes of stresses, because compaction and initial reorientation happens under greater stress levels, right? So that is the reason you have sigma 3 values. It's we'll talk about it at 15 psi or 103 kPa. Sometimes, depending on other methods, it can go up to 300 kPa. Load pulse 0.1 second duration. People talk about 0.5 to 20 hertz. Again, that depends on the relative difference between rest period and loading period and stuff. And then the loading can be using two different methods. One is called constant confining pressure, which is the most common thing you see. And then the other one is called variable confining pressure. And we'll get to that in a little bit. Okay. Well, we'll get to that right now. This is what you see, Astro T307. Yes. Frequency should be lower. Ideally, yes. Ideally, if you're trying to do that, but the method just uses the same frequencies. But you are right. The compaction speed is very low and stuff. So you should have probably load pulse depth width should be wider. So this is for Astro T307, and this is how this plot is. So this is horizontal stress or confining pressure in this case, and then you apply, this is in PSI folks, so just bear with me. This is basically 21 kPa. You can multiply by 7 on an approximate. It's 6.9 but close to 7. So 3 PSI you apply, and then your deviator stress is 3, 6, 9. Okay, at the same value, at the same confining pressure, you load it by 3. Okay, so let's go over the procedure first, because otherwise this is going to be difficult for you to understand. So in the procedure, you have stage 0. This is going to be stage number 0, and we are going to call it conditioning. Okay, usually it will have some kind of a sigma 3, some kind of a sigma d. We'll look into that, and then we're going to take n is number of cycles. Okay, so something we'll look into that. But conditioning is usually 500 to 10,000 cycles. What I have done most commonly in my life is 1,000 cycles conditioning. There is requirement that after conditioning you should not have permanent deformation more than this and stuff like that, but with a well compacted sample, 1,000 cycles usually work. Then you go to sequence number 1. Folks, these who are being exposed for the first time, this is going to be important, because this is very important to understand resilient modulus. Stress sequence 1, and I'm talking about the very first one, and just write down units please, because I am much more familiar with these numbers. I can go quickly on this. It's 3 psi, 3 psi, and you apply 100 cycles, and every cycle is, how long does it take? 1 second. So the test, this sequence takes 100 seconds, which is what? 1.5 minutes, 1 minute 50 seconds, right? Then you go to 2, keep 3 psi, deviator goes to 6, again 100 cycles, keep then 3, keep 3 psi, deviator goes to 9, again 100 cycles. Okay, after conditioning, how many sequences did we just talk about? 3. There are 15 such sequences. Okay, we'll look at the values, and in the tutorial today also we'll look into that and stuff. So after conditioning, don't worry about conditioning. The test has right now 3 sequences right now, and during the sequences, what did we do with the confining? Kept it constant. Hence, the test is called CCP, constant confining pressure. Okay? And then the next step is going to be 5, 500, and we'll go to that. No need to write this down. But again, we'll have 4, 5, 6. It's going to be 5, 5, 5. So again, another 3 with the same constant pressure. That's 35 kPa basically, 21 to 30. I know you're calculating if 5 is correct or not, but yes, it is correct. That's what 5 is. So 5 is constant confining pressure. Again, number 3. So do you now understand the top graph, what is going on? 3, there are 3 data points. 5, there are 3 data points. 10, 3 data points. 15, 10 data points. 20, 10 data points. 5 times 3 is, so that's 15 cycles of constant confining pressure. So the slope is vertical, I mean infinity basically, the lines are vertical. There is another method called NCHRP 1-28A, which actually says that, hey, that's actually not a very right characterization of your material. In your material, you should not keep constant confining, you should change confining as well when your vertical stress is also increasing. So in this case, your slopes don't stay same. It's 3, 6, 9, 3, 5, I don't know why, or is it 6? I don't remember the numbers. Don't get me on that. And then 10, 15, 20, it actually, as the y-axis increases, the x-axis is also increasing. Okay? So you can do this. This actually is meant or is supposed to be a better representation of actual testing or actual what happens in the field and stuff. But it was not really widely adopted or anything, but we still have a document called for this. Okay? That's the concept of VCP, variable confining pressure, because the lines are not vertical anymore. It's changing from state to state, it's changing. Now the question is, I still haven't defined to you, how do you calculate resilient modulus for people who are new to this method, right? How do you do? For every cycle, what do you have? You have basically this. Why am I doing this? I have already, well, maybe I should not do this. I should have the axis here. So you have already moved past, you are somewhere here. Now you are in a hysteretic loop. For every cycle, you have sigma d and you have epsilon r. So for all 100 cycles, you can calculate mr, which is sigma d over epsilon r. But the test procedure says that out of the 100, you take the last 5. 96, 97, 98, 99, 100. That 5, you take the average, that is what your resilient modulus reported is. For every cycle or for every stress sequence, you take cycles 96 through 100, take the average value of, did I write it somewhere? Average of sigma d of epsilon r for each of those cycles, and that you report as your resilient modulus for that sequence. How many sequences are there? So how many resilient modulus values are there? So if I ask you what is the resilient modulus of this material, what do you say? It depends. Tell me the stress state. What stress state is it? Right? E is equal to 30 ksi or 30,000 psi. That's a elastic representation. That is not resilient modulus. Right? Resilient modulus is not one value. A material cannot have a single resilient modulus. You can take a representative modulus. That's a different thing. We can talk about that tomorrow. Today we'll not have time. I will probably talk about that tomorrow actually. And you will see is representative modulus is different because you are trying to take one value to represent. It's like this, right? What is the average, like what is the height of a student in this class? It changes, right? So you have to take an average, or you have to take a 50th percentile, whatever you want to do, right? You're doing something representative. But that's what resilient modulus is. This is what VCP is. This is what CCP is. And test setups, traditionally, when systems were developed, and I think that's true for even the system that you still have the out external LVDT, right? Yeah. The simplified one I have is also external LVDT. Your LVDTs are outside on the system. It's not mounted directly on the specimen like this. Okay, but in Astro T7 allows that. Astro T307 allows external LVDTs. But if you go to NCHRP 1-28A, the harmonized, it says do not have LVDTs outside. You have to have LVDTs on the specimen. That's because there can be rotation of the specimen, there can be compliance of the loading load and stuff like that and stuff, right? So this is how. And if you do axial LVDT measurements, you should have it at 120 degrees across the specimen, three LVDTs, so that you measure rotation or tilting and stuff like that. Just a representation. Again, 60 repetitions per minute. There is a reason I don't say 60 hertz or whatever. I mean, I don't say 1 hertz or something, because that's not really what very well defined. There is another thing that I did not tell you. When you load a specimen, I said your confining pressure. Let's just go to the very first stage. Okay. Sigma 3 is equal to 3 psi. Sigma d is equal to 3 psi. Okay. What did I say about? Okay. Oh, by the way, is this a stress controlled test or a strain controlled test? Stress controlled, right? Because you are not specifying how much strain to apply or how much deformation to apply. You are telling how much stress to apply. So strain to measure, exactly. Strain you are measuring. It's not control. Talking about what are you controlling it, right? So it's basically you're telling your car to go at 60 miles per hour, and then you are measuring your fuel economy, something like that, right? What are you measuring versus what are you controlling? Now my question is, yesterday if you paid attention, I alluded to this. I said a device only knows how much to move because displacement is an absolute measurement. This is 0, this is 1, this is 2. It's very easy. Force is not an absolute measurement. Force is dependent on my material. If I'm trying to push and my hand is moving, force is 0. Whereas if this is constant, it's very big, right? So the question is, even if it is a stress control test, in the background the machine is actually going by movement. There is a problem with that. 0.1 second is this, very quick, right? And now I am trying to target 3 psi, 5 psi. You will see the maximum value is 40 psi, right? You have to do very quickly this, and when you do that and the sample comes or the rod comes and it hits it, the sample is not just deforming by the applied load, it is actually deforming or getting damaged by the impact, right? Which is not good. You don't want that. Your truck is not jumping on the road. The truck is applying a seating load and it's pushing against the load, right? So the question is, how do you ensure that? You always apply what is known as a seating load. So for every deviator stress, it's usually 1/10 of it is seating and 2.7 is the actually mechanically applied pulse load. Why? What happens if the seating is 0? Raki, what happens when the seating is 0? Think about the specimen and the rod. What happens when the seating is 0? No. How much? What? This is my rod. This is my specimen. Seating is 0. So is it touching? No. So you're losing contact. And then you're coming and banging it. So the moment you have seating is 0, you're going to lose contact in your feedback system. You never do that. That is the reason your code or your testing method always has a seating in there. Seating in there, right? So that's what this is. Seating load is 0.1 of the deviator, target deviator. So that's something that you really need to do. Okay, I've already told you this. Again, experimental people who are getting into design, testing and stuff like that, when you don't meet the shape, when you play with what is known as PID settings of your test systems, it actually tells. Because what is a feedback system, folks? Think about it this way. It's very simple. A feedback system is, it's like your you guys are all young. Has anybody ever had an antenna on your TV? Do you even remember what an antenna of a TV is? Right? Have you ever had to go up the roof and rotate the antenna to catch signal? So a feedback system is that. Aaya kya karke, you're just rotating, right? हाँ आ गया रुक जाओ, basically. That's essentially what it is, a feedback system, right? You're just trying to go back and forth, back and forth, back and forth, right? So the point is, if your feedback system is not giving you a good load pulse, then you have to adjust what is known as proportional integrative and derivative gain of the system, or PID system. That's equipment design. We are not going to go into that. Told you this already. Second modulus, load distribution, sample preparations. Specimens are, dimension is dependent on particle size. Those who have tested subgrade soils, you're probably talking about 2.8 inch diameter or 4 inch diameter, which is 100 mm or something like that, diameter. And then the height is usually double of that, 100 by 200 or something. Aggregates, they get bigger. To have a proper representative, you should have at least 4 to 5 times the Dmax and stuff. So for aggregate testing, the minimum you can do is 4 inch if you have a fine grained aggregate. The moment you have a bigger grain, you are going to 6 inch diameter. 6 inch diameter by 12 inch tall, which is pretty tough to work with usually and stuff. But that's what specimen preparation is. Okay, this is our stress sequence for type 1 or unbound aggregate materials. So I told you this, so you should now be able to read this with me. So 3 psi, 3, 6, 9, 5 psi, 5, 10, 15, 10 psi, 10, 15, 20, 15 psi, 10, 15, 20, 20 psi, 15, 20, 40. What did I just say? I just said the psi numbers. You just divide by 6.89, you will get those numbers. That's what I'm saying. Okay? That is what a full unbound aggregate test setup sequence ASTO T307 looks like. Make sense? Should we test subgrade soils under similar stress values? Where is the subgrade in the pavement system? Yeah. Question? So go ahead. Can we do for bound materials? Yes, you can do, but these stress states are defined for unbound aggregates and soils. Bound materials, It's a good question, and it can actually be very, very long discussion. What do you mean by bound materials? Because if it is bound material, if it is 100% bound, technically it is not stress dependent anymore. Stabilized material, yes. Stabilized materials, yes. I haven't tested. Have you tested it? Do you apply similar stuff? Yeah, but you're probably talking about very less percentage of cement, right? I mean, talking about 2-3% cement or something. It's I have never run those tests, honestly. So okay, and do you apply confining like similar stuff? Okay, okay. So people do it, but ideally it should also stand without confining. I don't know if confining pressure has an effect or not. I mean, my knowledge is going to be literature based. I don't have personal experience running stabilized. Very less. It's probably non-existent because it is standing by itself. But does the modulus depend on stress state on that? Whatever you tested, is it still a stress dependent material? It is, okay. Yeah, I haven't tested stabilized ever. So I hope that answers your question. So they're applying similar load levels, but we don't have like special specifications, at least to my knowledge. Oh, so this is the University of Illinois. Okay, this is another interesting point that I did not say. Okay, before we talked about this table, I forgot talking about this. This is the conditioning. The conditioning is done at sigma 3 is 15 psi and sigma d is also 15 psi. So what is sigma 1? 30, right? So let's define a very crude term. It's called torture index. Okay, how much are you torturing the sample? And torture index is defined by sigma 1 over sigma 3. How much confining you are applying versus how much large vertical stresses you are applying and stuff like that, right? So in this case, in the traditional conditioning, it is 2, right? 30 divided by 15. Yes? If you are trying to shake down a material, if you're trying to get rid of all the permanent deformation and all completely rearrange the particle and stuff, research has shown that if you do increase this value, it will actually shake down the material really well, it will actually pack it really well, and it will actually become a lot stronger, as long as it's not failing and stuff. I mean, you can't apply a ratio of 8 and stuff. That's going to probably fail. So what they did is, this is actually another of Professor Thompson's work. He actually did sigma 3 is 103, but sigma d is 310. So 310 divided by 8 is what? 35? No. What's that? By 7, sorry. 45, right? 310 divided by 7, it's basically 45. 45 psi. So what he did is 15 psi of confining, but he applied a deviator of 45 psi. So it's holding the material really well, but it is just pushing it really hard to pack it really well and then get a well compacted, well conditioned resilient modulus response under this torture index of 4.0. So basically, remember yesterday how we calculated subgrade soils and stuff? They are not very well confined because it's only about half a psi of confining pressure we calculated yesterday and stuff. The whole idea is during compaction, the more you push it, the more you condition it, the more of a resilient behavior you will get. So that is how this was defined. Again, this is a research test method. It is not a specification. So you can't written ASTO and stuff. It was just a research method, and it was developed. So again, this is the same setup I showed you yesterday. These are the LVDTs. This is the shear strength. This is after shear strength testing. Usually, by the way, you probably, if you look at the test specification or even your vendor equipment manual correctly and stuff, usually resilient modulus is a non-destructive test, right? It is much very small strain levels. So you can actually, after resilient modulus, you can actually run a shear strength test on that same sample, as long as you don't have LVDTs mounted and stuff. If you don't have it, you can run the same shear strength and you get 2 data points for one specimen. So this is after running the shear strength test. It's 11:12. You want to take a break now? I think we can take a break, because now we are getting into test results. I think the procedural part is over. We'll get into test results and then we'll get into models and stuff. Let's take a 15-minute break and come back. Thanks. So let's take any questions on whatever we had. I talked to a couple of you already, but any other questions? Yes. Ideally, it is okay. Good question. Will the resilient modulus change between the 2 test procedures? Probably yes, right? Because now it is much shaken. But what is more representative of what is happening in the real field? Their argument is that the higher torture one is actually more representative, because you are actually shaking it under bigger stresses. So that's the reason I said it's not a specification test, right? It's a research test. So maybe the numbers are different. I don't have the comparison. So let's take a look at some data, and then we're going to see some factors, and then we'll get into models. We should be okay in terms of time, because I want to get to know models for sure. So this is 4 different materials. CS6 is a typical dense graded aggregate based material. Ca11 is more of a sub base material. There is P gravel stuff, and you do optimum water content. The T80, T180 is your modified compactive effort in terms of kilonewton per meter cube and achieved water. This is something, again, experimenters, you need to really understand your optimum water content and the dry density. This is the density established. When you're doing modulus test, don't just report this, always report the achieved values, because that is what the sample actually knows, right? There's also a very big difference, those who are working with aggregates especially, very big difference between added water and actual water retained in the sample, right? Never ever report just added water, because water drains. So when you are testing, after that, collect sample. I used to just take the entire sample and put it in the oven. Much easier. So that way there is no question of did you take a representative sample. I just put it in a big tray, throw it in a big oven, get it next day. It's my actual tested water content, right? Don't just report this because it's not correct. Okay. This is how you plot resilient modulus. Many different ways. This is plotted on deviator stress. So think about it this way. What did we say? 5 different confining pressures and 3 deviator stress per confining pressure. So for a resilient modulus test, you will have, for a given material, you will have 5 different lines for deviator stress, right? And it should ideally, and we're going to talk about that bulk stress and stuff, it should ideally increase as the stress values increase for a coarse grained granular material, stress hardening material. Crushed stone, it goes all the way up to say 350 in this case. So 350 megapascal is about what? 50 KSI, 50,000 PSI and stuff, which is on the high side, I think. my maximum values probably have been something around that range and stuff. Okay, type 2, subgrade materials, right? Now we are talking about finer grained materials, and they're subgrade mostly. Now the question is, somebody can say, hey, if my base is actually like up in the pavement, also I have a fine grained material, of course, test it using whatever the stress states are applicable and stuff. 2-inch, 2.5-inch, 4-inch, typical. Can you run a 6-inch sample? Of course, yes, but you know who have run big samples, it's very difficult. So you always try to avoid size effect while at the same time making it representative. Compaction is different. How do you compact? Aggregate testing people, how are you compacting your samples? Vibratory, like a jackhammer kind of thing? Is that what you're doing? Okay. Standard. It's very difficult, by the way, sometimes to let's have a little discussion. How do you target density for your samples? How do you do that? Speak up. How do you make your sample? How do you specify target density and how do you meet it?